Okay, assalamu alaikum everyone. I am now trying this Zoom application for recording of my lecture, and this lecture will be about the next subtopic of this chapter, local searches, and our subtopic would be hill climbing algorithm. So just give me a time so that I can show you my slides. Here are the slides. So these are the things on this slide that we have seen previously. We have got the concepts about shoulder, global maximum, local maximum, flat area, which is called plateau, and some other things. So these concepts now we are going to use in the hill climbing algorithm. So, but first, uh, we will try to get some understanding about the hill climbing. So we know that this hill climbing algorithm is lying under the category of local searches, and which also means that it is no doubt a local search, but it is also optimal in some sense. I am saying this statement uh, with a quite care because it has some issues you will see, and we can apply this hill climbing algorithm to many problems. For example, you can apply this algorithm to build the noughts and crosses game. You can also apply this hill climbing algorithm to perform various tree search operations, and how this hill climbing algorithm normally runs. So in this hill climbing algorithm, it's a very short algorithm. I can just show you that you can see on this slide that this is a very short algorithm, just 3 or 4 lines, uh, in which we have some initial state, and then by starting from this initial state, we are going towards the next neighbors according to our cost function, or you can say if you are considering cost, then again there is a concept of finding the local minima or finding the local maxima, or finding the global minima or finding the global maxima. This algorithm has some issues. We will see these issues when it will come, but normally it continues from the starting state, and it will select those neighbors which are suitable. For example, if you are climbing a hill, then the suitable next state would be the higher state than your current state. So if you are finding a higher state from your current state, then you can go to that higher state. And after that, that higher state become your current state. And then if there are some other neighbors at higher locations, then you can select some optimal or best possible neighbor available, and then you can go to that point in a similar way by selecting that state as a current state, and in so on you can go on to the top of the hill, which is uh, your local maximum if you are searching for the local maxima. Similarly, we can apply this hill climbing algorithm in reverse direction. For example, we can find the local minimum if we just change this condition here. So let's come back to this previous slide, and we will see what this slide is saying, what this slide is giving some concepts about the hill climbing algorithm. So this is the first point in saying that in the algorithm we have a loop, and that loop will remain continue in the direction of increasing value, and that increasing value would be the value of your cost that you are considering. And if you are forwarding in uphill direction, then this loop will terminate when you will reach at the peak of that hill. And at the peak of that hill, you will not find any other neighbor with a higher value. So then your hill climbing algorithm will terminate itself. And in the process of this hill climbing, as we already mentioned that in local searches, we are not storing the whole path. So similarly, in this algorithm of hill climbing, we will only record the current state and its immediate neighboring nodes with the value of the objective function only. And this objective function, again, it depends. Either you are going towards the local minimum or you are going towards the local maximum, which is in the uphill direction. So I mentioned earlier that there are some issues with this algorithms. So what are those issues? Number one, hill climbing is good for finding a local maximum. And now you can understand what local maximum means. So local maximum means, for example, on this slide, you can say this is the global maximum and these are the local maxima. So hill climbing, if this is your current state as highlighted here with the circle, then the maximum help you can get from this algorithm of hill climbing is that you will reach at the top of this small hill, and that top of the hill is called local maximum. It is not possible for us to reach at the global maximum if we are going to start from this point. So this is some other thing, that if you will get your starting point here, then we can reach at the top of this higher mountain, and then the top of this higher mountain is again the global maximum. So this can be happen, but this is something other issue. I don't want to discuss this here at the basic level of hill climbing algorithms. So the first issue with the hill climbing algorithm is it is only good for finding the local maximum, and it does not guarantee that the best possible solution. What is the best possible solution? The global maximum. So global maximum is always our best possible solution, or always our best goal that we want to find. So by using this hill climbing algorithm, it is not possible for us, not 100%, but it is not possible for us that it will give us global maximum. It will not give us the optimal solution, you can say, but it will give us some solution, maybe near to your 100% solution that you want. And that's why we are calling that solution a local maximum. And the second issue with this algorithm is that it can get lost on plateau, or it can get lost on why we are calling this that it can get lost on the plateau, because that plateau is a surface area, is a flat surface area like this one. And if you have, maybe I have a pen here. So just give me the time. I am not finding any pen here, but yeah, but let's see. Let's try this one. No, these are the shapes. So what I can do. mm, 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 mm. So I can use this one. So for example, this is the flat area, and if this is the state here, and again if this is also a state here, so now you can understand that these two states are at the same level, or in other means that these two states have the same cost at the top of this plateau. So if I am here at this first node, then the algorithm will remain continue, and it will find the next neighbor, which is again at the same level or at the same value, and there is no any improvement in the value of the cost. So it will get stuck, it will stop here, and it will give us this state as a local maxima. So this is what it means here on this second point. So I'm just going to close it, and I want to move on my next slides. So now, so this was the last point. We have seen that this algorithm might get lost on the plateau, and now we are going to see the algorithms. So we can see that the hill climbing normally takes the problem, any kind of problem on which you will be able to fix it. So that problem will be the input to this hill climbing function, and it will return us a state, a node, and that state would be a local maximum. So we are not hoping that this algorithm will give us the global maximum, because we don't know where we will get the initial point. But if we manually or explicitly get our initial point on the higher mountain, and if that mountain has no any shoulders, then we will surely get global maximum. But this is something, another discussion. Maybe in your higher classes, you will see these discussions on the variants of the hill climbing algorithm. So the next state is saying that you have to identify the initial state of the problem, and then you have to store that initial state in a variable that is called current. So now that initial state is becoming the current state in this algorithm. And then this is the loop that we were talking about in the previous slide. So this is the loop, it will remain continue, and these are the three statements under it. So what this statement is saying? This statement is saying that so you will find the successor of this current variable. What is that current variable? This current variable is the same that you have taken in the or you have set in the previous statement. So you will find the neighbors, immediate neighbors, or you will find the successors of the current state. And after that, you will find the most suitable, or if you are going to find the highest state, means if you want to reach at the top of the mountain, or if you want to reach at the local maximum, then you have to select the highest valued states from the successors. So if you have 3 or 4 successors, then the successor with the highest value will be stored here in this variable neighbor. And then in the next step, you have to check the value of the neighbor with the value of the current state. That is, this is the current state from your previous statement. So if the next successor or if the next neighbor value is less than the current state's value or equal to the current state value, then what it means? Then it means that the next neighbor value uh, has not higher value, or the next neighbor value is equal to your current state. So in this situation, you are not finding any improvement because your direction is uphill. So you are not finding any improvement. So in this situation, what this algorithm will do? In this situation, this algorithm will simply return your current state. This means that your current state already is in a good situation, and there is no suggestion by this algorithm for you to get some improvement. So that's okay, that's fine. And now we are going to exit from this algorithm without any improvement. But if your next immediate neighbor value is higher than the current value, in other means, if this condition is false, then what it means? Then it means that the next neighbor has the higher value. And then what we have to do now, we have to update the next neighbor value into this current variable that you are seeing in this statement. So you have, now we are storing the next neighbor value into the current variable, and then we will again go on to this loop which is still going on. And then we are again finding the successor of that current state. And if we will be again in a situation that we have some higher valued successor, then you have to take that as a neighbor, and then you have to compare this condition again. And if the neighboring value is higher than the current value, you again have to update the value of the neighbor into the current, and then you have to continue this loop again. And this loop will remain continue as we are seeing. And what is the point, or where is the situation when we will come out from this algorithm? That situation is only when we don't have the higher value of the neighbor with respect to the current state's value. And when this situation will occur, we will simply return the current state and we will exit, or we will make an exit from this algorithm. So this is very much simple algorithm, just like you're finding a maximum number in an array, you can say. Or if you want to perform this hill climbing algorithm in reverse direction, which means if you want to find a local minimum, then you have to find the minimum number in an array. So that is simply an hill climbing algorithm. So this is the pseudocode. Now we will move on to the I think the last slide about the hill climbing search, on which you are seeing that there are different variants of hill climbing search are available. Variant means different versions. And because there are the issues with the basic version of the hill climbing, so people had a work on this basic hill climbing algorithm, and they made some other extended version. And one version is called stochastic hill climbing. Other version is called coordinate descent ascent hill climbing, you can say. And then the third one is called random restart hill climbing algorithm. And you will see the details about these variants in your uh, next classes. Um, but anyhow, for the moment, what is the difference between the basic hill climbing and the stochastic hill climbing? So the difference is only the random selection of neighboring nodes with respect to the basic algorithm. So we know that in hill climbing, in the basic version of hill climbing, we don't have any random selection. As you can see from this algorithm on this slide, there is no any random function here. So, but in stochastic hill climbing, we have this random function available in the pseudocode of the hill climbing. And through this random function, you can select uh, the neighboring nodes, the successors, randomly. And that is the difference between the basic hill climbing search that you have seen now in this lecture and between the stochastic hill climbing algorithm. And now the second is the coordinate descent ascent algorithm. Some people also call it gradient descent ascent algorithm. So uh, to understand it completely, you can join my classes of natural language processing, or you can see my lectures uh, on the topic of logistic regression. But here, according to your class and the audience and the level of the class, level of the students, so I am just going to give a brief introduction about this coordinate descent ascent algorithm. So in this algorithm, uh, no doubt we have to focus on coordinates. And what are those coordinates? Basically x and y. But the more important thing in this approach is the slope. Is the slope and at any position on the curve or on the surface. For example, if it is a hill climbing, and if we are talking about hill climbing, and we are talking that we have some kind of a version of coordinate descent ascent in hill climbing, then we can imagine in our minds that we have some kind of a hilly surface, like you have here. And again, I will use this annotate, but I'm not finding something very much straight so that I can draw some line. Let's try. So yes, good. Okay. So I am drawing this line. So this line is basically the slope of this curve. If my point is here at this point. So now you can imagine that this is something x-axis and this is something y-axis. And you have some values here, for example, 5, for example, 10, and for example, 15. I'm just trying. And so on, for example, 20. Okay. So now, so this is now the point, and this is the slope. Slope is just an normal slope that you normally see in your real life. For example, this is the slope. Slope normally elevates from the surface level to some highest level. So this is something a slope now, you can imagine. So this slope is increasing in this direction. And for at this point, if I will if my next state, if my, for example, if now again you have to uh, understand that either you are trying to find the global minimum or the global maximum, or the local minimum or the local maximum. So with respect to these terms, the concepts will be different. So for example, I am going to find the global minimum, then that global minimum would be here at this point. So, and if my next state is here or here, and in this way, like here. So by increasing the x coordinate, what I will get? I will get this point. This is the next neighbor of this uh, current point. So this is the next, or simply the successor. So if I am finding the global minimum, then at this slope, if my slope is decreasing, then this is the point that I am going to find the global minimum. If I have to find the global maximum, then my slope value would be in an increasing fashion. You can understand. So for global maximum, you have to go along with the increasing value of the slope, and for global minimum, you have to go along with the global for the, if I want to find the global minimum, then I have to consider the decreasing value of the slope. So, and these increase and decrease in the slope, you can calculate from the x and y coordinates. That's why it is called coordinate ascent and descent. So now come back to that thing. So this is called simply the coordinate descent ascent approach, in which so maybe there is something eraser or like that. So let's see, clear all drawings. Yes, thanks. Okay. I have to shift it a little bit higher so that you can see what behind it. So yes, so now I can continue. So in coordinate descent, ascent approach, you have to search along the coordinates, and you have to change the value of the x or y coordinates of the variable, and then you have to either descend or ascend accordingly, and finally you will find your goal, either it is global maximum or global minimum. So the last, which is the random restart hill climbing. So this is very much easy to understand. The other name for this random restart hill climbing is the shotgun hill climbing. Random restart. Its name is very much clear that in this approach you have to restart it randomly, and for example, this point here highlighted in red, we have to this random restart hill climbing iteratively does hill climbing, means it will perform the hill climbing basic operation iteratively in iterations, and in each iteration, each time you have to select randomly some initial state or initial condition. For example, if you are going to run the basic version of hill climbing for the first time, you will select some initial state, but that selection would be random. So okay, you have selected some random state, and I can, for example, perform this thing on the, and if that random state, I find it, for example, here my annotation is not working, so I don't know. So let's see it. Yes, it is now working. So now I'm going back to that slide. So it is, this Zoom is a little bit difficult to operate, and in the next lecture I have to practice it with all you students. So let's see. So for example, if I will get again this, and anyhow you can understand it. I don't want to waste the time here in just learning this Zoom. So if I will get my initial state here randomly, and after performing the basic hill climbing algorithm, I will move on to the higher states, and I will reach here at the local maximum. So this is something, the best solution up to this point I have find with the first with the first run of the basic algorithm. So, but this is not something I am searching. I am searching for the global maximum. Then again, according to a random restart hill climbing, or according to shotgun hill climbing, I will restart this operation again with another, possibly another initial condition. So I will restart the hill climbing again, and uh, in and this is now my second iteration, and it is possible that in my second iteration I will get my point here, I will get my initial state here, and this would be randomly. Keep this thing in your mind. So again, after getting initial state from initial state here, after processing the basic hill climbing, I can reach at the top of this hill again. But again, this is local maximum, not the global maximum, and this is not something I want. So what I have to do, I have to restart the hill climbing again. And if I am lucky, then maybe I will get my initial state here at this point, um, and this is my third iteration. We are assuming, uh, and if I will get my state here, and after performing the hill climbing basic version, I will reach at this global maximum. So this is the symbolic representation of the shotgun hill climbing. So, but one thing was left in the discussion that is coming into this point. And what is that point? So, for example, in our this example, we have performed random restart hill climbing, and we performed 3 iterations. And in each iteration, we will keep our solution, and then we will perform another iteration, and if we will find some better solution, then we will keep that better solution in the memory, and we will discard the previous solution. And similarly, for example, in third iteration, we find the global maximum, that which is the better than the previous one. So we will keep that global maximum, and we will discard the previous one. So that is also the point which I missed in my previous discussion. So here it is explained here. So the best solution is kept if a new run of hill climbing produces a better than the stored state. So it means that you have to keep the better solution in the memory, and you have to discard the previous version of the solution from the memory. And with this approach, because we have a random restart uh, option here in this version of hill climbing, so due to this random restart, maybe we will get our state at the hill where at the top of that hill the global maximum is available. So then we will find our global maximum, and that is something we needed. So this version of the hill climbing has resolved the issue of get sticking on the local maximum. So that's the mentioned in the last point, that we can get rid of local maxima. So among these three variants, this random restart hill climbing is something that you can keep on restarting again and again until you will reach at the global maximum. So this version will surely give you the global maximum, random restart hill climbing. But the stochastic hill climbing, again, here we are not sure that we will get our global maximum or global minimum. But this coordinate descent or random restart, uh, these approaches will give you your global maximum and minimum. So this is again the end of the hill climbing search, and then in the next lecture I will start with the simulated annealing. So I will not continue to the next subtopic because I want to make my video short, and so that it would be easily accessible to you. So until then, goodbye and Allah Hafiz.